All right, so I think we'll get started. Hello, everyone, and welcome back to the SNAPP seminar series. Today, we're thrilled to have Professor Mohsen Bayati to give a talk on estimating interference effects via distributional dynamics with his wonderful group. Mohsen is a professor of operations, information, and technology at Stanford Graduate School of Business. He's done a lot of important work on data-driven decision-making, experiment design, and the safe deployment of AI in areas such as healthcare, and has received many awards for this work, including the Healthcare Application Society's Best Paper Award and the 2016 APS Best Paper Award. So without further ado, I'll hand it over to Mohsen. You can ask questions via the chat, and you can also raise your hand during the talk.
Thank you, Ali, for the kind intro. Yes, feel free, anyone in the middle of the presentation, ask questions, interrupt me. Okay, so this is joint work with this great group of collaborators. Sadek, the first author listed here, is most of this work is his PhD dissertation, and so I'll give the reference at the end. Okay, so I'm going to start with a motivating example. So the motivation, there's a lot of motivating examples for this problem that we're going to be studying, but one that particularly I've been looking at with the group is, imagine, so this problem of intestinal worm infections, it's been a problem that has been actually very well studied with the framework of randomized experiment and interference. Basically, it is a major issue, and also it's an issue that is addressable by very low-cost medication, meaning some low-cost medication can actually substantially reduce the occurrences of them. But then, any of these programs, like if you want to potentially, I keep using the word deworming program, and that means like effectively doing mass deworming, like going to, for example, a country that the problem is prevalent, like in Africa, and then potentially providing the medication a few times a year to every child attending a school. And the challenge has been, what is the ROI of this program? Is it worth it? It's a lot of effort. It has costs. Is it going to be effective? Particularly on variables that are important, like school attendance, cognitive performance. And that's been the challenge, that how do we measure success? And of course, a well-known method of measuring success in something like this is a randomized clinical trial. And in this case, what would that be? So you randomize, let's just say, I don't know, some number of school children, and you offer a subset of them like a randomly, like I call this like the treatment group. They receive the medication, and the control group doesn't receive the medication. And you observe the outcomes over time. And one thing that ended up occurring initially during the studies of these type of trials was that there was no statistically significant difference in the outcomes of the two groups, even though the medication actually reduces the occurrence of the disease. But like for the outcomes that, for example, would support investing in this program, such as a school attendance, the difference was not significant. And in fact, a very well-known study in over 25 years ago concluded that there is no benefit, at least with regards to those outcomes that they were interested in, to invest in such programs. And then a little fast forward, a few years later, Miguel and Kremer actually did correct for what's known as a network effect, and they did show there is benefit. And let me elaborate, what do I mean by network effect? So here, the individuals that are our control group, you would expect in a classical RCT, randomized control trial, the control group doesn't interact with the treatment group. So if for example, the medication benefits the treated children, then let's just say they participate in school more. So you would see a big difference, or like some statistically significant difference between the school attendance of treated children and control children. But when they interact with each other, what happens is if this child benefits from the medication, then they won't transmit. So this is actually like the interactions of children with the environment is what leads to the kind of, for example, disease being transmitted. Like, to be very more specific, for example, kids playing in the same lake. So a sick child can basically transmit the worms to the other children. So this means when they are interacting, if this child benefits from the medication, then those who also interact and they are in the control group also benefit from the medication. Therefore, you won't see really the difference between the two outcomes of the two groups, even though the medication was helpful. So that's kind of the problem we're trying to look at. How do we make the measurement more accurately? And in fact, this problem has been very well studied in recent years, not just because of the example that I mentioned to you. There's a lot of other areas that this problem comes up in marketplace-related experimentation, where, for example, there is a shared supply or demand. There's been quite a bit of literature on this problem very recently for these kind of modern online experiments. Now, what do we want to look at in this talk? So we want to look at two specific problems. One is, so a lot of, as I mentioned in a bit, a lot of studies recently on this problem, normally there's an assumption that you observe who is interacting with whom, like which two, for example, children are actually interacting. You observe the network. That's the assumption. So we want to relax that assumption that what if we don't observe the network? And it's a very, and of course, this has also been studied, but substantially less than the other version where the network is observed. And then the second objective is, one challenge is, imagine you have been working on this problem and you have a known estimator, or you have a known algorithm to measure the effect of, for example, medication. How do you know your algorithm is correct? It's been a challenge to having access to data sets where you know the ground truth and you can measure success of the algorithm. So one of the other objectives here was to kind of release several benchmark data sets with no ground truth so that one can test different algorithms. Okay, so now before going to more details, just from a very high level, one factor that we will be trying to utilize is, okay, we don't observe the network, but what we are going to be observing is outcomes over time. So what I mean by that, so here, there's a network, one child is treated, and so because this child is treated, like let's just say we are at time period 1, in time period 2, the neighboring children also benefit from the medication. And, time period here in this example of deworming could be a matter of maybe months or weeks, but sometimes it could be a matter of minutes. It depends really on the application. How long will it take for the effect to propagate through the network? And then over time, this propagates till eventually settles to what I call an equilibrium. And in fact, most of the studies, so this actually, here's a place to list a large body of literature, and I probably am still missing a subset that has been looking at this problem. And the common theme, one is normally system is observed at the equilibrium, meaning you assume everything, this effect has propagated and has settled into an equilibrium. And also, a lot of times the network is observed or also is assumed to be sparse. The more dense the network, estimators normally have worse variance. So now there's a subset of this literature that actually, like what we do, they do look at outcomes over time. And the general motivation behind this is that, yes, the system hasn't settled, for example, here, but there's information if we observe the outcomes over time. So that's the motivation behind this set of papers. And that's what we're going to be using. Before I move to the rest of the presentation, any question about the problem? Okay, so here's a plan. I'll spend 3 minutes to give the high-level intuition of the approach, and then explain the theoretical model, and then we'll show you several examples. Like I'll show you applying this method to the Miguel and Kramer's data set, 2 online experiments during collaboration with Amazon, and some simulations using AI agents, as well as the data sets that I was mentioning. And there are, of course, this methodology that we will be describing doesn't work always, and I'll try to go over those limitations as well at the end. Okay, so high-level overview of the approach. This is through an animation, and I'm gonna repeat this animation 3 times. Each time I reveal more information. So think this is a network. Let's just hypothetically, this is a network of children. And so what happens is as time progresses, like for example, we are treating larger fraction of them. So initially maybe like 25%, then 50%, then 85% are treated. And now, one other thing that we're going to track is let's just say each child has an outcome variable of interest. And let's just say outcome variable of interest is, for example, it's like a continuous variable or like an integer variable, which is like measuring their attendance to school. Then for a large group of children, we can look at the distribution of that outcome variable. And this is how it would evolve over time. And so we can actually look at this number. Even though we don't see the network, we can see this distribution changing over time. And very specifically, we can look at the average of this distribution over time as we are treating more and more of the children. And in fact, here it's more concretely visible. So there are 3 stages to this experiment. Stage 1, roughly 25% are treated. Stage 2, 50% are treated, and stage 3, 85% are treated. And notice that you do see even the phenomena of, so here's the average of outcome. Let's just say outcome was some measure of participation. So this is increasing over time. So what I mean is, the moment we treat 25% of the children, so their participation increases across all children. This is, control and treatment combined. It is increasing, and then eventually settles, reaches an equilibrium. And then now we ramp up again the treatment, and then again it increases and it settles, and then ramp it up again, and eventually. So we do observe this data, and the goal is to use that information. And I'll give you 2 more slides, and then finish with kind of this intuition part. So we are tracking this distribution over time, and kind of the underlying result is that there exists a function f, which is invariant, and at any time overall, this function f is what maps these distributions across time. Now, of course, this is not always true, and we do study settings that this doesn't happen, but for most of the talk, I think it's easier to assume this is the case. And of course, under several assumptions, we do prove such a result. And that's kind of the main ingredient for progress. So the moment such f exists, then you can apply machine learning, because we are observing, again, very high level, we are observing samples. Like, what is a sample? A sample is like any distribution at one time and then in the next time period. And then I can, if I have repeated samples, then I can try to estimate the function f. And the moment I estimate the function f, I can now replay the data or the experiment. You see that this is an experiment where initially 25% were treated, then 50, then 85. So now I can replay the experiment with the estimated F, and I do two counterfactuals. One counterfactual is when everyone is treated. So this is when everyone is treated, I replay. And then another one is when no one is treated. And I look at the difference between these two, and that gives me the measure that I'm after, the total treatment effect. And you can measure different counterfactuals too. Like, for example, what's the difference between if 80% are treated versus 20% are treated? But for simplicity, let's just focus at this one. So one function f hat learned from a single experiment generates all counterfactuals. So that's really the high level kind of overview of the approach.
Mohsen, can I ask a question?
Yes, please.
Okay, this is a very cool idea. What exactly are the inputs and outputs of the function f?
Yes. Okay, I'll make it more clear in a bit. But,
okay, cool. That's fine.
But think about it distribution. So, and what is distribution? I have these children's outcomes at time t and at time t plus 1, right? So think of two histograms. I have literally two histograms. So the input is one histogram, the output is another histogram. So that's kind of the high level. But more concretely, in fact, we will be mostly using mean and variance of those two.
And is pi part of the input to f, or
oh,
pi
yes,
is...
yes. Also
okay.
pi.
Okay, good. This
yes.
makes perfect sense now. Thank you.
Apology. Yeah, thanks for clarifying. Yes. It will become more clear.
And most like one thing might be that even though you treat some number of people, the other neighbors who get sort of, they change their label could be sort of, there could be selection effect, but you're sort of looking at problems where that doesn't happen. That's why the distribution is a good summary of.
So this is a randomized experiment. We are the one who are choosing who is treated, and we are selecting that randomly. If this thing is an observational study, then we cannot apply this methodology, of course. Does that make sense?
No, that's true. But like, so the neighbors of the treated people could sort of also adopt a label, and that can change the future dynamics. And there I was saying there could be some selection effect in who are the first set of neighbors who get influenced. But you're assuming some sort of stationarity or homogeneity in the F function.
Yes. No, that is what we are trying to model. Like what you described is what we are trying to model. And the idea is in a large kind of N regime, a substantial averaging will happen, and you will be able to make progress.
Okay, thanks.
But of course, you will see the model has assumptions in it. So the assumptions can be violated. Any other question? Okay, so let's now define the formal setup. So capital N is the number of units or children, let's just say, from the deworming example. And then there are capital T time periods. At each time period, each unit, so I will always refer to the units, and T will be referring to time. So each unit will have a treatment variable, and this means whether they are treated or not. Now, and then this is Y will be the outcome. So this will be the outcome of child I at time T. And so what we really have once the experiment, so first of all, because we are the ones who are experimenting, we get to choose this matrix W. And for example, in time 0, okay, no one is treated, but then time 1, maybe like this child is randomly selected, and then more children are randomly selected. One thing I want to note that for an application like deworming, the child is treated, they stay treated. So the randomizations coming from who is added to the pool at each time. But in some applications, like in, for example, ride-sharing applications, if what you're experimenting with is an algorithm in the backend that the user cannot detect, then you can, each time period, you can just randomly select a subset of like the entire population and choose their treatment assignment. So meaning people can switch from 0 to 1 or 1 to 0 as well. depends on settings. So the kind of experiment that I have here is a staggered experiment, and the other ones are kind of a micro-randomized trial or Bernoulli randomized experiment. The results that we have apply to both. That's the main point I wanted to mention. So you choose this matrix W, and these are the outcomes that we observe. So that's all the data that we want to work with. Then the objective that we want to measure is the difference between these two counterfactual scenarios. The outcomes when everybody is treated, except of course time period 0 that we start, that's our initial condition, versus when no one is treated. So we look at all the Y's and notice that we are looking at the Y only in the last time period. And this is if we are interested in the equilibrium method once things settle down. So you look at the Y's of everyone at this time period, average them, minus Y's of everyone at this time period and average them. So that is the quantity that you want to estimate. And now here is where I'm going to introduce, because the result that I mentioned that there exists that function f needs some assumptions. So the model that we will study to kind of measure, capture kind of these interactions is this model. And let me kind of elaborate. There's an equation version on the right, and then there's the figure version on the left. So the way it works is so this is all the children, their outcome in the prior time period. So I've noticed that I'm trying to look at the child I's outcome at time t+1. And the point is to say this outcome is a function of all children's outcomes and treatments in the prior time period, and very specifically the same child's outcome and treatment through a different route. And I'll try to mention what these are. So think about, there exists an unknown function G. G is unknown to us. There exists an unknown interaction network, which is modeled with a random matrix. And you can think of this random matrix as, there's a random graph and it's an adjacency matrix, and we have normalized it properly. And the way it works is, so each child's treatment and outcome are input to a function G, and then that function is multiplied here through, as you can see, this equation is multiplied by this kind of weight or matrix weight that measures the interaction of child I and child J, and they're added together. So, and that's the network effect. So this part is the network effect, but then you could imagine when you treat a child, that child will get a direct benefit, and this is captured by this component, which is kind of the direct effect. And so the most important thing is all of these are unobserved. H, G, and all these A's are unobserved by us. And now with this setup, the result is, so the very first result is, if the matrix A's entries are IID, Gaussian, with this mean and variance, and of course, we do have a result when these means are not the same per entry, but just I try to simplify the equations a little, and I'm just looking at a common mean. But these means can be different. Then what happens is, as n grows to infinity, there exists a function ft. Notice that it is a function of time at the moment that depends only on these quantities, that maps the mean of time t and the treatment. This is what fraction are treated. This is to your question, like the pi to mean at time t+1. And by the way, this is just a function of the mean. The actual result includes mean and variance, but for simplicity, I'm just going to use the one for mean. If you want to see the formal result, it does look like something like this. I'll mention it for a second, but I'll come back to this slide. So the very formal result is something like this, where you have these test functions that, like you could literally apply mean and variance, but this is this quantity, basically, the empirical the joint distribution of treatment and outcome at time t effectively converges to a Gaussian and a random variable w, which is kind of a weak limit. And the function f is really here. So as you can see, it's mean and variance of time t are mapped to the mean of time t plus 1 and variance of time t plus 1. That is like the overall version of function f. But again, for simplicity, I want to just focus on this one. So there's a function ft that maps mean and treatment fraction to mean in the next time period. So there's a lot of assumptions here, right, which you would want to question. But before going further, let me make sure the type of result is clear. Any question about the result? Okay, so that is a result. Now, one thing, notice that this function f is a function of t, and the reason is we have this function g's that we are allowed to be a function of time, h we are allowed to be a function of time, and even these mu's as variances technically are allowed to be a function of time. I have removed that dependence for the moment for simplicity. But then when we get to later, we have to estimate f. We do need to deal with this time dependency component, which I'll get back to. Before going forward, I want to mention, where does this type of result come from? So this type of results are actually coming from literature in approximate message passing algorithm and statistical physics. It's not a new result that we've proved. This type of results have existed before. So the kind of the most classic version is kind of this TAP equation that has been introduced and later emerged in the literature from approximate message passing. And the idea is, you want to measure, for example, the free energy of a system, where this free energy of the system is an aggregate measure of a large number of small interactions. And the evolution of free energy as a parameter is changing, like temperature is changing, so the machinery, like this machinery that, like the TAP equation, is very similar. It looks at kind of this distribution changes and gives us an equation very much like the equation we saw in this slide, like the TAP equation. So this type, and this is a very small fraction of the literature. There's a large body of literature that has evolved. I can tell you the major difference between what we do and this literature is the following, because this is worthwhile to discuss. What are we trying to do differently? So in this literature, normally what happens is A is actually not unknown. A is known. And what they do is they actually select the right G. So it's all about select the G. And when I say literature, I'm specifically not talking about the approximate message passing literature. So there, the focus is on, with a known A, pick a G such that Y satisfies specific properties. And to be more concrete, for example, Y's are an optimization algorithm's variables, and like gradient descent. And like imagine you have an n-dimensional vector that you're applying a stochastic gradient descent to, and then you want to pick a specific kind of denoiser in the process, and that denoiser is G. So you pick the right G such that the algorithm converges faster or has better properties. So what we do is quite opposite in the sense that we don't know A, we don't know G, we don't know H. What we do see instead, we actually see Y. So Y's are already, we don't have a control over them. The only control we have over Y's is through selection of treatments. But then from this observation, we get to estimate the aggregate effect of these. So that's like so it's the same type of result, but used completely differently. That's really kind of a good way of compare what we do with that literature. Okay, so let me now talk about the estimation strategy, and this is where I'm going to simplify things again because you will see why. Okay, so I think the cartoon that I showed at the beginning, what kind of a bit more formal version of it is here. So there are these functions f, and once we estimate them, then we can apply ft recursively and obtain any counterfactual. And of course, this part you would expect that if you did estimate f correctly, then you can estimate counterfactuals correctly. So this follows from the previous result primarily. But then the bar is primarily on estimation of f, and for estimating f, you would need additional assumptions. So let me give you a concrete recipe that you can actually apply. So here is an experiment that has 3 stages. There's a stage 1 where, let's just say P1 fraction are treated, and then there's a stage 2 that P2 fraction are treated, and a stage 3 that P3 fraction are treated. But then we are putting a very specific function h and g here. So this is a function where is tau times treatment plus an interaction term between treatment and outcome. And notice that it's not a function of time anymore because these gamma and tau are not a function of time. So I already made an assumption that is ht is constant. And here again, for G, I'm making an assumption that G is constant, the meaning doesn't change over time. And then the moment I do that, I get an equation like this, that the average outcome at time t plus 1 is this primarily linear except this interaction term of mean and treatment fraction and the prior time period. But the moment you make this assumption and you have this functional form, and what do I have? What is my observation? My observation is these nus and these pi's over capital T time periods. So as long as I have 2 different values of pi, I should be able to estimate these quantities using linear regression in them. That is, of course, with this simplifying assumptions. Okay, so this is a way of estimating, like it's a very concrete recipe that you can apply. The challenge with this is, of course, I made a bunch of assumptions, and also you may say, well, what if the functional form you're trying to estimate is not linear, it's potentially a more complex function, and then you have capital T time periods only to estimate. So some of these like online experiments are at most like 50, 60 time periods. So I have 50 observations effectively to estimate potentially more complex functions. So that's one challenge. The second challenge is, what if these things are time dependent? So, but number one, the first challenge is more of an issue, which is limited data to estimate more complex functions. And here is where we introduce this idea of we call it distribution preserving network bootstrap, but from a very high level, the idea is, everything we did so far was I was looking at the average of the entire population, right? But what if I take subpopulations? So looking at all of the children, so this was the distribution, but what if I look at two different subpopulations, and these subpopulations could, initially you can assume they are selected completely at random, but in reality, you can actually select them such that in one of them, a larger fraction treated than the other one. And this still maintains randomness because treatment is random. So here, then I have, for example, two subpopulations. One has more treated than the other one. And I can apply exact same machinery to each subpopulation. So effectively, like in this picture, I have doubled the sample size. And if I have more and more subpopulations, and notice that these subpopulations do not have to be non-overlapping. They can potentially overlap. So we have a theoretical result that shows, let me see, do I have the real result that shows that you can get the same type of theoretical state evolution that we have. Like you can get the same type of equation, but across these subpopulations. So we have the number of sample size becomes capital T times the number of subpopulations. So this is giving us a slightly more, so the formal result is something like this. So there is this superscript S, which, by the way, this is the same as pi. So I'm replacing pi and p here. So you get this type of equation. For every subpopulation, the average of that subpopulation is a function of the prior time period's global average and the same subpopulation average. So this way, we get the number of subpopulations times the sample size times the time period samples, and you can have a more accurate estimation. Okay, so that's kind of the high-level view of the methodology. Before I go to the actual numerics, is there any question? So let's see how it works in a couple of experiments, and we can come back to the methodology as well. So the first one is going to the deworming example. So this is y-axis is considered it's a measure of increase in participation of children to school. And the data is about 30,000 children. And notice that the number of time periods is 5. So this is where really even the linear regression method is not very effective, in fact. So this new version that looks at subpopulation is what we ended up using. So what I want to show you here is that Miguel and Kremer, what they did was the following. They showed that by looking at the network interaction specifically, of course, they don't have all of the network, but they have partial observations of the network. And the partial observation is looking at where the children live, and the children who are living closer to each other, they're assuming they're interacting with each other. So by making that correction, they're able to show that 19% participation increases if they didn't if they account for that factor. So think about the following. This baseline is, imagine you have no network information. This is how much you will be able to measure participation improves. And by factoring the network information, you can actually measure, no, participation improves 19% even more. It's just you were not able to measure it if you didn't have the network information. Oops. So that is how network information allows you get a more accurate measure. What is a true value of participation? We don't know. It could be 14%, like 0.414. It could be much higher. It could be lower. But they, at least from their result, claim that this is a lower bound. It could be higher than this. In fact, the paper, they argue that their estimate is a lower bound because they cannot measure interactions of children that live further from each other, but potentially could be using the same water resource. And we apply this causal message passing methodology that I described to the one with subpopulations, and we see 36% increase. So it is aligned with what they say, but at the same time, we cannot tell you that our number is correct exactly because we don't know ground truth. So the caveat that I was mentioning at the beginning of the talk still exists, but it is nice to see that it is aligned with, at least it is greater than equal this number. So that's the first validation that we can see. And just to elaborate, this is how Miguel and Kremer really does. Think of, ignore this. So imagine like a fancy way of doing this treatment effect estimation is like writing a regression where you say yi is a linear function of who is treated. So that's a fancy way of doing the same thing. And then they add this additional term, which shows how many children in the proximity of each child is treated. And this addition term is what allows them to go from here to here. So this is, and it requires knowing the neighborhood. Now, the exact same methodology, we have actually applied this in 2 experiments at Amazon. And here I'm not allowed to show numbers, but I can show you qualitatively. So I have, again, 3 methods, very much like here, 3 methods. Basic method that doesn't have any network knowledge, a method that has network knowledge, and our method that doesn't have network knowledge but have access to outcomes over time. So the basic method for one experiment with 7,000 units and 100 time periods, it estimates a negative effect, and it's not statistically significant. The network-aware method, which adds, it's a slightly more nuanced version of what I showed you, the regression method, actually estimates a positive effect, and it shows it's a statistically significant. So the sign flipped, but most importantly is statistically significant. And then our same methodology gives you a similar result. And another experiment, again, sign flipped, but of course, none of these are statistically significant, but that was another example of the results between these 2 being aligned. And the takeaway is the network-free approach reproduces the network-aware results in 3 experiments, 2 here in an online setting with this type of N and T versus the deworming example. So that's the real data experiments. The big caveat is we don't know the ground truth, meaning it could be like someone can say that, both of these methods can be equally wrong, okay? So that is still a possibility. So how do we then go about testing this method? And this is where we introduce this. This data is available online. There are 6 environments where we'll very much real-looking data sets. Some of them are real data sets, but we are simulating an environment with them just to show you qualitatively, like in one of these examples, like we see results of this type. So here, this is like a data set based on New York taxi data. So we do see a ground truth, and these are 2 versions of our methodology. And these are 2 baseline estimators, difference in means and Horwitz-Thompson. And as you can see, like both of these are underestimating the true effect, and this one is aligned. So that is, I will not go through any of these because I want to give you another example, which is actually motivated by this one. And I will give you that one in more detail. But I want to kind of encourage everyone who wants to test their methodology, they can utilize any of these 6 data sets. So let me talk about this this simulation that I want to go over. So we have, so the idea behind this is, how do we, sometimes even running an experiment itself is very expensive. In healthcare, it can be unethical, it can be legally constrained, and there's a lot of factors. Is there a way, a lot of factors that can make running experiments expensive? So is there a way we could somehow avoid running the experiment but get the results? So this is an objective that is completely unrelated to our talk. Our talk was about estimation with interference, but for the 2-3 slides, I'm going to take a slight detour of talking about this second objective, but then I'll come back to the interference example or objective. So here, the idea is, can we replace a real-world experiment with LLM-based agents? So what is the explicit experiment we used? We try to replicate. So there is a 61 million person experiment that Facebook ran in 2012, where they wanted to see effect of messages on a social network on users' self-reported voting. So, for example, there are two treatments. In fact, these are two it's a treatment. It's an experiment with 3 treatments. One treatment do nothing, and one treatment show a user an informational message like this. So this is a message that the user would receive. And the third treatment was no. Not only they would actually be given which one of their neighbors would vote. So this is the experiment they ran. And we thought, how can we replicate this experiment with LLM agents? So what we did was we picked 20,000 LLM agents. These are variants of GPT 4.1 series. But to kind of make them more representative of population, so we took US Census data, and for graph, we wanted a real kind of a social network graph. So we picked this Twitter following network. So it's not Facebook, of course. And then here, each specific user is one API call to an LLM agent. And one other thing we do is, even though we started with Twitter network, but then there's this warm-up period that each of these users, which effectively a copy of ChatGPT, is we're letting them to change who they want to follow. They can, based on their census data, we tell them, generate your interests and select your close friends and political stance even. And then this goes through the warm-up period. And one other thing is that there are 3 types of agents here. And the idea was, some agents may be more politically sophisticated. So these are like each one of these 20,000 is one of these 3. And so here's an example of a user that some information coming from the census, and then these are what the user ends up selecting during the warm-up period. And now, one other thing we do is we want to observe things over time. So the same user will be observed over time, and as if we are trying to model whether they log in or log out. So after the warm-up period, we experiment this over 40 days up to the election day. So each day, and one other thing is we let the user decide when they want to log back in next time. And so you can see there's a content feed 4 days to the election, the user is seeing that. And then the treatment is they would see something like this. How likely are you to vote in the upcoming election? And of course, showing them the treatment, the informational treatment and the social treatment. So now let me show you the results. Before qualitatively, one thing that happens is, remember, there are 2 treatments. One is social, one is informational. in the Facebook experiment, the social treatment was much stronger than the informational treatment, and we do see the same thing. But of course, we're also seeing the effect that is 10 times larger in our experiment than the original experiment. So clearly, it's not an absolute replication of the experiment. It's only replicating the direction that the social is more effective than the informational. But this wasn't kind of the main. Remember, I said this is just a detour for a couple of slides. I want to come back to our goal, which is the interference effect. So both of these treatments, you would expect to have interference effect because on the network, users are interacting. When you treat one of them, you're impacting their neighbors as well. And but then because we are running the experiment, we get to measure the ground truth. So the ground truth here, this is for the social message, and the experiment is 3 time periods, 20%, then 40%, then 80% treated. By 3 time periods, I mean 3 stages. It's all of them are 40 time periods. And here is one, we see that the methodology, and in fact, I didn't put the difference in means and Horwitz-Thompson, but they underestimate the effect. And but then on the other treatment, so one thing is, by the way, the social message is a very strong effect. On the informational message, we see the causal message passing, our approach overestimates by a large margin. And this is actually a failure mode, which has a very good reason why the methodology wouldn't work for something like this. And that is because of the following. Because we are running a simulation, we also are observing a version where nobody's treated. And even when nobody's treated, people's voting intention increases over time as they're getting closer and closer to election day. So this is a setting where the outcome has a trend over time. And when outcome has a trend over time, and you can start guessing, if I'm ramping up treatment over time, and outcome itself is increasing over time, so how can I disentangle the two? It's impossible to disentangle the two unless I create one of the two things. Either I have periods large enough that treatment is not ramped up. Like, for example, you see like the initial, let's just say 10 periods or 13 periods, 20% are treated. If this was longer, then I would be able to see that this trend is not the trend that I'm trying to, it's because of the treatment. Now what happens is the methodology is based on a machine learning method. And when the true signal is weak, like here, and this time period for each stage is not long enough, it can effectively overestimate the true effect. Versus here, the signal is strong, so it won't overestimate the effect. So the failure mode is if there is a trend that is there is not enough signal to disentangle it from the treatment ramp up. And this is primarily an issue with experiments that are a staggered treatment, not experiments that I get to ramp up or ramp down. If I get to ramp up or ramp down, it's a lot better. So that's kind of the failure mode that I wanted to elaborate on. And with that, let me just summarize. So this is a framework for experimenting under network interference. It is inspired by these techniques from statistical physics and approximate message passing. And several of those simulation-based 6 data sets that I was mentioning, to the outcomes are evolving according to nonlinear dynamics, and it seems to be effective. And there is some evidence that this methodology could be useful on real data sets, and the references are here. And with that, I'm going to stop for questions.
Thank you, Mohsen. Thanks for the interesting talk. So should we, are there any questions in the chat? Maybe I'll start with one question. So I wonder how much the the model and the approach you describe here gives some justification for like an approach that exists in the RCT literature, which is to vary the intensity of treatment locally, and then have linear models that account for this variation, this as a correction for the interference. So it's not exploiting per se the staggered rollout and the percentage of treated, but it's leveraging the fact that you can vary locally, for example, like the intensity of this deworming program, and try to tease out what is the nature of the interference from that. So I see an analogy there. I don't know if it's something you explored and whether this gives theory to justify this.
So what do you mean by locally?
So for example,
Because
that in some villages you have more or less of the schools or like of the budget, you vary the budget locally. So it's like you vary the intensity, but you know it, that's part of your design.
Oh, right. Okay, so I see. If I understand your question is instead of picking like a universal, say 20% is treated, you say, no, I'm gonna have a different distribution for the treatment. So I can give you a short answer, which is the results, the theoretical results on the state evolution, which is the equation, whether the function f exists. Those results don't need this treatment variable to be having kind of a universal.
Yes.
Basically, you can have a distribution as long as the W, the treatment distribution, because by the way, treatment doesn't even need to be binary, it can be continuous for that result. So if you have a continuous treatment variable and its distribution has a weak limit, as n goes to infinity, it converges to a weak limit, then you would, and which effectively allows you to have these variable locally. But the point is, there's a caveat. Point of the treatment is supposed to be random. So if it is correlated with certain covariates, then that's a problem. But assuming you do have like a separated that, you're allowed to have this treatment variable to have like a kind of a distribution. But when it gets to estimation, a lot of the results that at least we have are for this binary settings. So meaning there are two sets of results. There exists this limiting f and whether we can estimate it. So the latter, we have a lot more assumptions. And at least for the setting that you described, I don't believe we have result. But for the former, meaning the f exists, we do have result.
Okay, thanks. So maybe opening up to the group if there are other questions.
Maybe I can ask a quick question. Mohsen, you mentioned you have slightly more general results where AIJs are not IID Gaussian. So suppose for like a graphon, you also have some sort of results, but you don't observe the location of every node on the graphon scale.
So the results, these are not our results. Like, so the literature that I was referring to you, approximate message passing literature. So that literature have generalized to the following. The first natural generalization is when AIJs are IID, but are independent, but not necessarily the same distribution or Gaussian. Like, for example, they have the same moments as an IID setup. And then, so there are results for those. There are even results for rotational invariant distributions and a few more. The graphon version specifically, I don't think there is one, or at least I'm not aware of. There's a lot of papers, so I could be missing. But there is quite a bit of at least extensions beyond just Gaussian. Although I should mention there are two types of proof techniques. One category of proof techniques heavily relies on the Gaussianity, and it relies on this conditioning technique that Erwin Bolthausen came up with that we also use. And then there's another approach which uses the kind of what's known as a computation tree. It's like a combinatorial argument, and that's the one that doesn't use Gaussianity and uses the results are weaker but more general distribution.
So I wonder if I could just ask a sort of I think it's a follow-up to Varun's question, but what do I know? Close. So yeah, the motivation was where you had this sort of mu ij over n structure in the mappings, and that was to motivate the use of the transfer functions, the f's, which is really cool, right? It's really cool that they're doing this stuff. But I was thinking about that, and that does feel like there's a law of large numbers thing going on there, where as n goes to infinity, you're averaging over a tremendous number of other people in the population. But the kind of environments that you're describing for deworming and so forth, I feel like that's got a very local structure, and you wouldn't get that kind of averaging across the large population. Though you would still, I think, get a mapping through the distributions across a very large population where you'd be basically averaging a bunch of local environments. So did the results that you described capture that second framework?
So good question. Yes. So you're allowed. So remember I said the mu ij's can be different. So there are different forms of this result that has been generalized, but again, in the approximate message passing literature, for example, where you could have, for example, a network with clusters, and then each cluster has its own intensity. But because n goes to infinity and the number of clusters is finite, you do get the averaging given inside the cluster. And you can get the same type of mapping F, but it's a much more nuanced F in the sense that you need to track all the mean and variances across the cluster from one time period to another time period, but the same result holds. So those type of results exist. The version we have is allowing these mu ij's have their own limit. So imagine the means, the degree distribution has a limit. So then that shows up in the function F as a random variable. So
Thank you.
that's
That
another
helps.
form of looking at it.
Would that also capture the case where you have increasing numbers of clusters as n goes to infinity?
As far as I know, I don't think so. In fact, one thing that is good to think about, at least majority of the papers, this type of results are really operating on the mode of, for example, the time period. One thing we didn't talk about was t. So t is considered finite as n goes to infinity. If t and n grow together, a lot of this analysis gets more complicated, especially if you're thinking about convergence like this. This is something that I took for granted. Like I'm assuming this dynamic converges quickly. So what I'm trying to say is t is considered finite, n grows. As if any structure in the network, again, considered finite, whether, for example, the number of clusters where n grows. So if any of those kind of structural components also grows with n, as far as I know, there is no result. I mean, there are some smaller results, like for example, like there are results that like when even t grows, but slower than n for a special class of problems. But like there are, for example, finite sample n results for the convergence, which allow then a study when t grows as well. But the one that you described, I'm not aware of.
Thank you.
Are there other questions? If not, I'll thank again Mohsen, our speaker, for today, and we'll see you all in the next seminar. Thank you.
Thank you all.
Thank you, Mohsen.